A very good morning, students. Till now we have learnt about time and space complexity and how to calculate the time and space complexity of simple algorithms in terms of n, which is number of steps or the input size. And we have also discussed about the basic operation of an algorithm, that is the place where the most important operation of the algorithm is taking place, which leads to generation of the result. In this video, we will discuss about the best, worst and average case complexity of an algorithm. So let us start. First of all, let us try to understand that how an algorithm's complexity will increase if there is a change in the size of the input. Let us say that the total time of execution of an operation is COP for a algorithm's basic operation, and Cn is the number of times the operation needs to be executed for the given input size. So COP is the time taken for execution of the operation, which is dependent on the machine, and C of n is the total number of steps or operations that need to be executed for fulfilling the basic operation. Now, T of n is the total time that the algorithm is going to take. So obviously we can very clearly see that time of execution of one step is COP and total number of steps is C of n. Therefore, total time of the algorithm will be COP into C of n. So this formula we will freeze. It is equivalent. Why we have put a wavy equal to sign here? Because it is equivalent. We will not say that this is the exact time, because such a claim cannot be made. So we always work in approximations. Now, using this formula, we can estimate how much faster would this algorithm run on a machine that is 10 times faster than we have. In this, what we are trying to determine is how much efficiency will increase for the algorithm, how much faster it will run if we take a machine which is 10 times faster. Now the obvious answer that will come to our mind will be that if the machine will be 10 times faster, then the output will run 10 times fast. Now we assume that, let us give a value to C of n. So let us give it a formula of half into n minus 1. This is the assumption that, okay, this is the total number of steps that we are going to execute. Now, how much longer will the algorithm run if we double its input size? Now, if we increase the speed of the machine 10 times, then the algorithm is going to run 10 times fast. Now, if we increase the input size n to double, how much fast or slow the algorithm will run? Now, we have taken the value of C of n to be half into n minus 1, and we can open these brackets, so n square minus n, and we will multiply this half also, so we will get half into n square minus half of n. Basically, we have multiplied this n by 2 with this n minus 1. So we have got this value, and we will approximate it. We will take the highest degree of n and drop rest of the values over here. So we get half of n square. So C of n is equivalent approximately to half of n square. Now what we will do is, we will compare T of 2n, that is when the input size is doubled, with T of n, when the input size is n and 2 of n. So this will be equivalent to COP, which is the cost of an operation, into C of 2n upon cost of operation into C of n, which is equivalent to, okay, so we have C of n is half of n square, so we will put half of n square, half of n square. But here n is 2n, so we will put half of 2n square, and here we will put half of n square. Now we will open this bracket, we will get 4 of n square. N square and n square will get cancelled, half and half will get cancelled. what remains is 4. That means if we double the input size, the algorithm will run 4 times longer. So that doesn't mean doubling the input size will double the decrease the speed by half, but it will decrease the speed by 4 times. That is what this calculation is trying to tell us. That this simply implies that the size of the input is going to influence your running time drastically, and it is not necessarily a simple calculation of 2 times increase means 2 times increase in speed, the calculation, but it is a complicated calculation in which we have to put the values in the formula and then calculate. Okay, now coming to the next related topic. There is an order of growth for a given function. Now, after answering the question that a slight increase in the input can make the performance of an algorithm vary a lot, for small inputs of all algorithms seem to work fine. A different running time for small input is not really what distinguishes efficient algorithms from inefficient ones. If it is a small calculation and one calculation is taking more time, the other calculation is taking less time, which is only slightly different from each other, and for small inputs both of them are running at the same speed, then we cannot really distinguish between which one is faster and which one is slower. Like we have taken the example of the GCD. In one method we are dividing the larger number by the smaller number, and the other method we are using the remainder calculation method, in which the long division method was used. Now if we take small numbers, then the complexity will not be very clear, but if we take very large numbers as input, then the number of times the calculation has to be repeated will become tremendously large. Suppose we have to find out the GCD of 2, 3, 5, 7, 4, 7 and 9, 9, 9, 8, 8, 8, 5. Now, for making this, for finding out the GCD of these numbers by the simple division method, in which we are dividing the larger number by the smaller number, the number of steps will be considerably less as compared to the long division method, in which the prime numbers are being used for making the divisions. So that way, if we are using huge input size, then the clear distinction between the two algorithms can be made. In order to confirm this, let us look at this chart. For an input size of n, suppose some algorithm has a runtime of log n, some has a runtime of n, some has a runtime of n log n, another has n square, then n cube, then 2n, then n factorial. These are the different run times, standard run times that the algorithms can have. Now, for an input size of 10, log n will take 3.3 units of time, n will take 10 units of time, n log n will take 3 into 10 units of time, n square will take 10 square, then n cube will take 10 cube, 2 raised to power n will take equivalent to 10 cube, and n factorial will take 3.6 into 10 raised to power 6 operations. Now, for 10 square, that is for 100, this thing is going to increase. And when we say for 10 cube, it will increase further. And for 10 raised to the power 6, we can see for 10 operations, it was taking 3.3, and for 10 raised to the power 6 operations, it is taking 20. And similarly here, for n square, for 10 inputs, it is taking 10 square time. And for 10 raised to power 6 inputs, it is taking 10 raised to power 12 time. So, as the size of the input is increasing, our different algorithms with different complexities, their time units are increasing in an exponential manner. They are increasing drastically. So, small change in input or change in the size of the input is going to have a huge impact on how your algorithm is going to perform. Next is the nature of the input. One is the size of the input, which we have seen is going to impact the performance of your algorithm considerably. Another factor is the nature of the input, whether it is the best case input, it is the worst case input, or the average case input. Now let us discuss these theoretically before going into the details. So the worst case complexity input is one in which the maximum calculations have to be done. Suppose we are sorting a list of numbers, then worst case input will be all the numbers are sorted in opposite order, and we have to resort the whole list in order to generate the proper sorting order. So if we are sorting 1, 2, 3, 4, the worst case input will be the answers, the list is sorted as 4, 3, 2, 1. So all the numbers have to be moved. And the best case input will be the list is already sorted. So our input list is 1, 2, 3, 4, and we are trying to sort it, and only the time will be taken will be in determining that the list is already sorted. And the average case efficiency is that we are not sure whether the algorithm, the list will get sorted in 5 operations or 10 operations. So we make a calculation, okay, in one operation how much time will be taken, in 2 operations how much time will be taken, 3 operations how much time will be taken, and if the input size is n, then for n operations how much time will be taken, and we add all these cases of first case, second case, third case till n case and divide it by n to get the average complexity. Let us understand these in a better manner. So for the worst case complexity, if in sequential search or linear search, we are searching for an element in a list of items, the running time of the algorithm will be different for the same input. Suppose the input list is this 2, 4, 6, 3, 1, 8, 9, 5. Now if we are searching for 2, which is the first number, the runtime will be 1. If we are searching for 5, then whole list has to be traversed, so the runtime will be 8. And if we search for a number which is not present in the list, the runtime will be n, because all the n numbers have to be checked. Then the best case efficiency is, suppose in a sequential search, we are looking for the item which is in the first place of the list, or in case of sorting, the best case will be that the list is already sorted. Then the average case efficiency is, let us consider the linear or sequential search. In this, let us assume that the probability of successful search is P, and the probability of the first match occurring in the ith position will be P of n. We are going to, if we are looking for an item and the successful search is there, then the probability of successful search is P, and finding the element in the ith position, because all the positions are going to have the same weightage. So probability of finding the item in the ith position is P upon n. Now the average case complexity will be, if we find the item in the first place, so 1 into P upon n plus 2 into P upon n plus so on n into P upon n for the finding the item in the nth place into probability of finding the item in the ith position, and plus we will do n into 1 minus p. 1 minus p is the probability of unsuccessful search. So n into 1 minus p is done. Now we try to simplify this thing. We take the p upon n common. So we get 1 plus 2 plus 3 plus n into 1 minus p. Now this 1 plus 2 plus 3 plus n, the formula for this for simplification will be n into n plus 1 upon 2. Now the n into n plus 1 upon 2 that we get here, the n, this outer n will get cancelled with the inner n. So we are left with p into n plus 1 upon 2 plus n into 1 minus p. So this becomes the average case complexity in case of linear search. and